here. So this is very normal. Tungsten oxide is first nearest, and second nearest is the tungsten, oxygen tungsten, bridging tungsten. But in the case of the molybdenum, very small peak is here. The nearest neighbor oxygen is disappears. But molybdenum interactions, bridging molybdenum is very strong. Where is the nearest neighbor oxygens? So our analysis is here, the Debye-Waller factors. The Debye-Waller factor is increasing by temperatures, but this absolute jump is come from the static distortions. For tungstens, all atoms are very similar atoms and increasing the temperatures. But in the case of molybdenum, only the O2. O2 means the nearest neighbor bridging oxygen has a very large distortions. Very large distortions. But the temperature dependence is similar. This means that we expected the Yan-Taylor effect of the long, short, such kind of distortions. After that, another scientist is conclude from the theoretical result that there is a Yan-Taylor effect in these systems. I'm sorry, this is the Yan-Taylor effect. That means. Finally, 10 minutes, I show you the obtain the potential curve from the analysis of excess temperature dependence. So I'll show you already the harmonic interaction potential. V is expanded to the non-perturbative type harmonic approximation or harmonic curve and third order. For this type of the most potentials, it has such kind of equations and expanded here. So the first harmonic part is here and the second part is here, both here. So we use the Debye-Waller factors of second Debye-Waller factors and third cumulant, order cumulant. So lowest order of the second cumulant is equal to the V2, means the harmonic part. Here, harmonic part. And the third order cumulant is almost same as the third order potential part here. So in the case of the most potential, d alpha cubed is this part. So we measure from x-axis this V2 and V3s and divided by these parameters, we can determine the alpha and d. This is simple one, simple calculations. So after that, we can reconstruct to the most type potential from the resultant d and alpha. That is the result. This is the this type of molecules. The chromium, from chromium to the 3D metals are central, and 3 oxygen atoms are coordinated, and these oxygens are exchanged in the bulk waters in the solution state. Many water molecules are around here. But the speed of exchange are very widely distributed. From chromium, for chromium, the exchange reaction is very slow, -6 times 1 second per 1 second. On the other hand, these ions has a very faster exchange. For example, the zinc 2 plus, it has a very fast 10 to the 8 times per second. So why these different widely exchanges rate? So our analysis from the X-ars, we measured and analyzed to the D values. And the D is plotted from the experimentalists is here, and this is the exchange reaction rate here. So there are very nice relations, and slower species has a very high value of barriers, Ds, right? Oxygen, water molecules over the very high, should be over the high barriers. But in the case of the faster ions, the D becomes very small and easily to go over to the and easily exchange. The cross point is the theoretical calculations using the molecular orbital theories by the Swedish researchers. The almost same tendency appears. This is the last topic for the application of exhaust thermal factors and determined to the such kind of bond potentials. We discussed the first days in the properties of nanomaterials. Finally, I summarized of these 6 lectures. The X-ars and nanomaterials. X-ars has a good many merits of for the nanomaterials characterizations. Non-crystalline, solid amorphous, inhomogeneous, and unstable. X-ars is shows a very strong point. It's a very nice merit. And X-ars detect the only local structures. So the nanomaterials is different from the crystal structures. It's very locally characterized. In the case using the X-rays and detection of also X-rays, so in situ or operant measurement is applicable. In that case, we can pursue the dynamic systems over some bonding magnetic. So the production of nanomaterials or changing of nanomaterials and chemical reaction using the nanomaterials, for example, the batteries. And recent development of the facilities. New synchrotrons. Also, old synchrotron is working well, but now new synchrotrons in high emittance. It shows a very coherent and small beams. So it's possible to the microbeam X-ars measurement, and the coherent and short pulsed X-ars it's possible to the time resolved pixels. So these kind of dynamics is more clear, and in homogeneous state is possible to the the nanobeam pixels can be appears of the inhomogeneous systems. So you can use this pixel system to the study of the nanomaterials or in the future. So in my image, my Ixas is not complete systems technique. XRDs and the Raman spectrum and IR spectrum, XPD, XPS, or every measurement facilities has every merit. So Ixas merit is one Ixas technique is applicable to many systems. So my image is this is Japanese samurai soldiers. One Ixas facilities is cut the magnetic systems and semiconducting systems and the nanomaterial systems and biological systems. Everything we can try to get a local structure system, local structure informations. So that is my image. What is your image for after my 6 lectures? Please contact me. So that is finished to the long lectures this winter. Thank you very much for your attention. Lunch is ready. You have any comment or comment?